Hi, I am Shahul Ami, working as Professor AC Department, Sales Institute of Technology, Karyapati. In this session, we are going to discuss about a problem which is related to state variable technique. This will come under linear control engineering. First, I will read the problem statement, then we will discuss how to solve this problem. A system is characterized by transfer function y of s by u of s is equal to 2 divided by s cube plus 6x square plus 11s plus 6. We have to test the controllability and observability of the system. So here they have given a transfer function. From that we need to find out differential equations related to this transfer function. Then from that we have to form state variable matrix. Using that we have to find out whether it is controllable or observable. Let's start with finding differential equation for this transfer function. So first step is we have to cross multiply that is denominator with y of s and numerator with u of s. So I will get s cube plus 6s square plus 11s plus 6 into y of s is equal to 2 into u of s. Now we have to take inverse Laplace transform to find the differential equation. The inverse Laplace transform of this equation is here actually s cube. So inverse transform Laplace transform of s cube is d triple dot of y triple dot of t, that is nothing but d cube y of t by dt cube. Similarly s square, so 6 y double dot of t plus 11 y dot of t and then 6 y of t is equal to 2 into u of t. Now we have to define the state variable. So here we are assuming that x1 is equal to y, x2 is equal to first order differentiation of x1 dot, which is equal to y dot, and x3 is equal to x2 dot, that is first differentiation of x2, which is equal to y double dot, and x3 dot is equal to y triple dot. Now we are going to substitute these state variable in the differential equation. So first one is y triple dot. This is equal to x3 dot plus 6y double dot of t. This is nothing but double dot is x2, double dot is equal to x3. Okay, so here it is x3 is equal to x2 dot is equal to y double dot, and then y dot of t is equal to x2. So 11 x2 and y of t is x1. So 6 x1, which is equal to 2 into u. Now we need a first order differentiation of the state variable. So I am considering x3 dot one side and the other things right hand side. So I am just moving this one right hand side. So I'll get minus 6x3 minus 11x2 minus 6x1 plus 2u. Now we are going to form state matrix. So here first I have to start with the state differentiation of state variable. First one is x1 dot, next one is x2 dot, and third one is x3 dot. Okay, x1 dot is equal to x2, x2 dot is equal to x3, this one, and the last one x3 dot is equal to, they have given an equation. Okay, based on the differential equation we have formed this equation. Now we have to form the state variable. State variables are x dot is equal to a into x plus b into u, and y is equal to c into x plus d into u. So x is x dot and u. So in all the state variable we have x, x dot and u. So I am just taking the first equation. First equation is x1 dot, x1 dot. In this equation we have only x2, the remaining x1 and x3 are 0. So I am just forming the first row as x1 is equal to 0, x2 1, x3 is 0. So first row of A matrix I have given this one, and second equation, that is x3 is equal to x2 dot, x2 dot. Here when you are seeing this, we have only x3, okay, x1 and x2 is missing, so the coefficient of x1 and x2 are 0. So the second row of a matrix is 0 0 1, and this is nothing but x2 x3, and this is x2, and this one is x1. The third equation is given here, x3 dot. Here we have all the state variable, that is x1 is there, x2 is there, x3 is there, in addition to that u also there, and the prior equation x1 dot and x2 dot, here this x1 dot is equal to x2 only, there is no u. So we have assumed that u, first row 0, second row also 0, because x2 dot there is no u. In the third equation x3 dot we have u, the coefficient of u is 2, so it is 2. The last row of A matrix is, the coefficient of x1 is minus 6, coefficient of x2 is minus 11, this is x1, this is x2, and this is x3, minus 6. So x1 dot, x2 dot, x3 dot is equal to this matrix, this is actually called A matrix, into x1, x2, x3 plus 0 0 2 into u. And similarly the output, this is actually called input equation, and output equation y is equal to cx plus du. Here in output, this is actually called output equation, that is y is equal to x1, y is equal to x1, that is the output is purely depends upon x1, state variable x1, and x2 and x3 coefficients are 0. So directly we can say that output is purely depends on state variable x1. So I am putting 1 in x1 place, and 0 0, and the state variable are x1, x2, x3, and this is output equation, and plus 0, D matrix is 0 into u, because there is nothing in this equation, there is, because y is purely depends upon x1 and it does not depend upon u. And we have found A matrix, B matrix, and C matrix. Using this we are going to find the controllability and observability of the system. So first I have written the matrix A, B, C, and controllability can be checked using composite matrix called QC, which is formed by, and this is called Kalman test, and is given a matrix, composite matrix, which is equal to B, AB, A square B, and it will go up to A power n minus 1 B, and n is number of state variables or order of the system. Here in this case we have 3 state variable x1, x2, x3, so n is equal to 3. So this composite matrix is reduced to B, AB, and A square B. Now after forming this composite matrix, we have to find the determinant of QC, and it should not equal to we have to find the rank of the matrix, and if it is not is equal to 0, then the rank of this matrix is n, or here n is equal to 3. Hence we can define like the system is completely controllable. Okay. Now first thing is we have B, and we have to form AB, and then we have to form A square B. First AB, we are going to form AB. So I am going to just multiply A and B. So I have put A matrix and B matrix. I am just multiplying. So first row and the column. So which is equal to in the column, this matrix we have 0 0 2. So the last one we have to multiply here in this matrix 0 0 0. So first entry is 0, second entry is 0 0 1. So when you are multiplying this row and this column, we have to multiply 1 and 2. So 1 into 2 is 2. The third row is minus 6, minus 11, minus 6. When we are multiplying this third row and the column, so this will become 0, this will become, and minus 6 into 2 is minus 12. 6 into 2, 12, minus is minus 12. So AB we have formed. Then A square B. A square B is equal to, we can do in two different ways. First here I have done like I multiplied A and A, then I multiplied with B, or you can do like A into AB. Already we have obtained AB. AB is here, so we can multiply A and AB, then you will get the answer. Here I just multiplied A and A square, and then B. So when I am multiplying these two things, I will get this one, and then we have to multiply with the B. So I get the matrix output as 2, minus 12, and 50. Now we have to substitute all these things in composite matrix. So when we are forming composite matrix, that is B, AB, and A square B, we get 0 0. This is B, and this is AB, and this is A square B. We get this matrix. Now we have to find the determinant of this matrix. When we are finding determinant of this matrix, so it is equal to minus 8. Okay, hence magnitude of QZ is not equal to 0. Hence we can say that the rank of this matrix is equal to 3. So this rank is equal to order of the system, or number of state variable n, which is equal to 3. Hence we can say that this is non-singular matrix. So if the determinant is not is equal to 0, we can conclude that the given system is completely controllable. Similarly, we have to check for observability. For observability, we have to form a matrix, that is Q naught is equal to C transpose, A transpose, C transpose, A transpose square, C transpose, and it will go up to A transpose n minus 1 into C transpose. Here n is equal to 3, because order of the system and number of state variable is equal to 3. When we are substituting the matrix, Q naught will be like C transpose, A transpose, C transpose, and A transpose square into C transpose. Now we have to find out, we have C matrix, and we have to find out this one and this one, and we have to form this matrix and find the rank of the matrix. That is, we have to find the determinant of Q naught, and if it is not equal to 0, then we can conclude that the rank of the matrix is equal to 3. Hence we can conclude like the system is completely observable. So we have C, this is C transpose. A transpose, C transpose is, we have to first find, we have to write the A transpose. You know what is transpose? We have to make all the rows into column into row. So this is actually A transpose and this is C transpose. When we are multiplying these two things, here we have 1 at the first element is 1 and the rest of the thing is 0. So this row will come as answer. So 0, 1, 0. Next we have to find out A transpose square C transpose. Here again this can be determined by A transpose into A transpose C transpose. So we have already determined A transpose C transpose. When you are multiplying these two, you will get this one. But you can do like this. But I have done like I have written A transpose and A transpose, and then I have multiplied with C transpose. When we are multiplying A transpose and A transpose, I will get this matrix, that is 0, 0, 6, 0, 1, 0, minus 1, and then 0, 1, minus 6. Okay, now now I am just multiplying. The result with so here in this case I have first multiplied this A transpose and C transpose, because we have already determined this value, this multiplication, that is A transpose C transpose. In the previous slide we have just a minute. So we have, when we are multiplying these two things, we will get the answer is 0, 1, 0. That is, here we have A transpose C transpose is 0, 1, 0. Now I am going to use this one, that is I am going to substitute this one here and I am going to multiply with A transpose. When I am multiplying A transpose and A transpose C transpose, I will get 0, 0, 1. This is simple matrix multiplication. You can easily work out this and we can get an answer. Okay. Now we have to substitute all these things in the composite matrix called QO. QO, here this is the first column and this is the second column, that is 1, 0, 0, 0, 1, 0, second column, third column is 0, 0, 1. So the composite matrix is Q0 is equal to 1, 0, 0, 0, 1, 0 and 0, 0, 1. Now when we are seeing this is the unit matrix, so the magnitude is 1. So we can conclude that the rank is 3 and it is equal to n. N is also 3. So we can say that this is non-singular matrix and the conclusion is completely observable. Okay. So this way we can solve this problem which is related to controllability, observability of a given problem. In this particular problem, we started with the transfer function and we have converted the transfer function into differential equation. Then we have defined the state variable. From that we form the matrix and we have identified ABCD matrix. Okay, D is equal to 0 and we have identified ABC matrix and we have substituted the value of these matrix in the composite matrix form for observability and controllability, and we have identified or we have determined the rank of the matrix, composite matrix. From that we have concluded that this particular system is completely controllable as well as observable. Thanks for listening. So if you have any queries, you just post in the channel. I will reply to that queries. Thank you very much.